In speech communication applications like hearing aids, knowing the direction of arrival, the DOA of a target speaker, is very important. However, estimating the DOA can become increasingly difficult as the level of background noise and reverberation increases. The main objective of this work is to estimate the DOA of a target speaker in a binaural hearing aid context, and we exploit for this also the opportunity to integrate an array of calibrated external microphones. Practically, this means is, given everyday like devices like smartphones or tablets, or even another hearing aid setup, how can they assist in estimating the DOA of the target speaker? I'm Daniel Fejgin, and together with Simon Doclo, we welcome you to our ICASSP 2023 presentation. If you're interested whether there is a benefit in exploiting these calibrated external microphone arrays, and if there is, how much the hearing aid setup actually does benefit from them, stay tuned. In general, in this work, we consider approaches that estimate the direction of arrival using a vector of so-called relative transfer functions, RTFs. And we do this because these RTFs actually encode the speaker DOA. Having available an estimate of such an RTF vector, we'll compare it against a database of unequivocal prototype RTF vectors for different directions, and select the direction that maximizes this RTF matching as our DOA best estimate. And of course, this RTF vector can be estimated using only the hearing aid microphones, or this RTF vector can be estimated using the hearing aid microphones together with the external microphones. What we propose in this contribution is to consider both arrays, not only for the estimation of the RTF vector, but to consider both arrays together also for the prototype matching of RTF vectors. To be more precise now, if we consider the case that no calibrated external microphone is available, the RTF vector estimate that we have considers only the hearing aid microphone signals. And we match only the RTF vector of the hearing aid microphone signals against a database of unequivocal prototype RTF vectors of only the hearing aid microphone signals. Mathematically speaking, we construct a one-dimensional spatial spectrum that we optimize. Now, if we are given an array of calibrated external microphones, then similar as for the hearing aid microphone signals, we also have a database for the external microphones. We can estimate the RTF vector corresponding to the hearing aid microphone signals, as well as the RTF vector corresponding to the external microphone signals, and then we can compare both RTF vectors against both types of RTF databases. Mathematically speaking, what we have here now is a two-dimensional spatial spectrum, and we perform a two-dimensional optimization. This figure here shows an example of such two-dimensional spatial spectrum, where each point corresponds to one candidate position as seen from the respective array, either the hearing aid or the calibrated external microphone array. And to further consider the potential of this proposed two-dimensional spectrum, we now consider the special case that we have prior knowledge about the geometry of the acoustic scene available. Now, we don't need to consider anymore all possible pairs of DOAs, but only those where both arrays, so to speak, see the same candidate position. And these candidate positions, they are shown here with these white crosses for the previous example. So mathematically speaking, we reduce the dimensionality of the problem from a two-dimensional towards a one-dimensional problem. To evaluate the benefit of exploiting calibrated external microphone arrays for assisted DOA estimation, we consider a second hearing aid setup as the calibrated array of external microphones. We compare 4 different algorithms, which are based on this RTF vector prototype matching approach, but these 4 algorithms, they differ in how the microphones are actually utilized. The first algorithm considers only the hearing aid microphone signals, both for RTF vector estimation as well as for estimation of the direction of arrival. The second algorithm, it considers both the hearing aid microphone signals as well as the external microphone signals for the estimation of the RTF vector, but the construction of the spatial spectrum is based using only the database of the hearing aid microphone signals. The last 2 cases consider the proposed approach, where we are now given 2 databases corresponding to the hearing aid microphone signals and the calibrated external microphone signals, so that we can estimate again the RTF vector using all microphone signals, and we construct a two-dimensional spatial spectrum in general, or we use prior knowledge about the geometry of the acoustic scene to construct a one-dimensional spatial spectrum in the special case, exploiting for both of these cases both databases. In our lab, we made separate recordings of speech and diffuse-like noise in a highly reverberant acoustic environment. We considered a dummy head equipped with hearing aids, and as already mentioned, a second hearing aid setup on a dummy head as the area of calibrated external microphones. We considered 9 different DOAs, and after recording, we scaled the noise to 0 dB signal-to-noise ratio. For further details about the setup, implementation, and algorithmic parameters, have a look at our paper, please. To assess the direction of arrival estimation performance, we average the localization accuracy over the considered 9 speaker DOAs, and the localization accuracy for each DOA condition is defined as the percentage of frames in which the speaker is correctly localized within a range of ±5 degrees. Coming now to the results, where we depict the average localization accuracy on the y-axis as a function of the investigated algorithms depicted on the x-axis. First, if we do not consider calibrated external microphones, such that no external microphone is used for the construction of the spatial spectrum, we do not see any significant improvements in the localization accuracy, just by considering external microphones for the estimation of the RTF vector alone. Second, if we do consider calibrated external microphones such that the direction of arrival is estimated from the spatial spectrum that is constructed from 2 databases, the estimation accuracy can be increased compared to not considering calibrated external microphones as in the first 2 algorithms. And third, if prior knowledge about the geometry of the acoustic scene is available, exploiting this knowledge can significantly improve the localization performance. With these findings, I would like to conclude the presentation and wrap up. We explored how calibrated external microphones can be exploited to assist in estimating the direction of arrival of a target speaker. We extended a recently proposed one-dimensional relative transfer function-based DOA estimation algorithm to a 2-dimensional prototype matching approach by exploiting the availability of a database of unequipped prototype RTF vectors of the external microphones. And we conducted experiments in a noisy and highly reverberant acoustic environment with recorded data, and the results showed a benefit when calibrated external microphones are exploited for estimating the DOA compared to no or only uncalibrated external microphones. In future work, we will investigate the potential of these external microphones to tackle the DOA estimation task also for multiple speakers. Thank you very much for your attention and enjoy this year's ICASSP.